Oh, yeah. Hey, Pierre, you hear me?
Yes, I hear you.
I don't hear you. Let me try. Yeah, can you try to say something again?
Can you hear me?
Oh, yeah, perfect. How are you doing?
Good. And
Yep.
you?
Good, thanks. You are in Zurich?
Yeah, currently, yes, I'm in Zurich, yes.
Oh, nice. I think people are coming soon, so
Yeah, we can wait.
people gathering up.
Yes.
Okay, let's wait maybe 2 minutes.
Yes.
Okay. How is Julia? Is she good now?
Yeah, she's better. I think she hopes to be able to give a talk tomorrow.
She won't able to, you said?
No, I think she will be able to.
She will be able to. Okay, nice.
Yeah. If it's still
hear.
better, yes.
Nice, yeah. Yeah, good to hear. Okay, so this. Okay. What are they? What are they not coming? Let's give them one more minute. Here, sorry.
Yeah, no problem. I'm just sharing my screen.
Yes, yes. How is Julia?
Yeah.
Maybe you already talked about it. I can ask this topic to.
Yes. Yeah,
sorry, I had to take a phone call.
No problem.
Huh? Okay, that's good. Okay, let's start. Let's start recording. Okay, now people are back. Okay, thank you very much for giving us your second talk, Eric. He's going to tell us about cluster varieties and fog contour of mirror symmetry.
Okay, so thank you very much. So indeed, my goal is to say something about cluster varieties and fog-on-shock duality. And so here I just have written down some list of references. Everything I will say is somehow contained somewhere in this paper of Gross-I-Can-Kill, fog-on-shock, contour chain, and Gross-I-Can-Kill concept. So the plan of my talk is first to give some kind of introduction to the topic of cluster varieties, and more precisely to the birational point of view on cluster varieties introduced by Gross-I-Can-Kill. Then I will give a very brief mention of how cluster varieties are related to the study of moduli spaces of local systems, which was one of the original motivation of Fog-on-Shock to study cluster varieties, and which was one of the motivation for the Fog-on-Shock duality conjecture that I will briefly review. And I will end by some result of Gross-I-Can-Kill concept on this duality conjecture. Yeah, so the most basic example of non-compact Calabi-Yau variety is maybe given by a torus, algebraic torus, C start with a D. So algebraically, it is spec of some ring of Laurent polynomials in D variables x1, xt. And it's Calabi-Yau because it has a top volume form, holomorphic volume form omega, which in local coordinate is dx1 over x1, wedge dx2 over x2, and so on. And cluster varieties are non-compact Calabi-Yau varieties, which are natural generalization of tori, in the sense that they will be obtained by gluing together tori along particular volume-preserving birational automorphisms. So we will glue tori together in a way which preserves this volume form, and in particular preserving the Calabi-Yau condition. So let me introduce some notation. Let's fix n some lattice with just some free abelian group, n is z to the power something. And let's call m the dual lattice. And let's denote by angle bracket the natural duality pairing between the lattice n and its dual lattice m. And then out of this data, we can construct a torus. I will denote by Tn the torus with co-character lattice n and character lattice m. So it is a torus which is spec of the group algebra defined by the group M. Okay, so concretely, the functions on this torus are monomials of the form z to the m with m in n. And now we will, as I have just advertised, we want to glue copies of this torus along volume-preserving birational maps. And so here I just wrote down an example of such volume-preserving birational transformation. So if you fix an element m in the character lattice m, and an element n in the co-character lattice n, and you assume that these two data, m and n, satisfy the compatibility condition that the duality pairing between n and m is 0, then you can define a birational automorphism of the torus by sending a function z to the m prime, monomial z to the m prime, to the same monomial z to the m prime, multiplied by some function 1 plus z to the m to the power pairing between n and m prime. So here, in this definition, m is used to specifying the monomial z to the m, which is here, and the n is used here to specify the power of this function. So it is clear that this transformation is some birational automorphism of the torus. So in general, it's not an honest automorphism because 1 plus z to the m can vanish. But generically, 1 plus z to the m does not vanish, and so this thing is a birational transformation of the torus. And the thing which is claimed here and which requires some check is that this transformation is volume preserving. Meaning if you compute this action on the holomorphic volume form, you check that this transformation preserves the holomorphic volume form. And you can check that directly, or maybe slightly different point of view on this property of this transformation is to realize that this transformation, you can think about it as a time one flow of a formal vector field written explicitly here. So what I mean is that a vector field is some kind of infinitesimal transformation, and you can integrate this vector field and look at the time one flow. So maybe formally it's something you could write as as exponential of this vector field. And you can check that the exponential of this vector field indeed produces this transformation. Or maybe I should explain the notation. So partial n for an element n in n, it's a vector field on the torus which act on, so a vector field act on a function, and it produces, by acting on z to the m, it produces a duality pairing between n and m times z to the m. So the torus invariant vector field in local coordinates is something like x1 times d over dx1. And the thing one needs to remark is that the vector field z to the m times partial n is divergence free if and only if this condition, this compatibility condition between n and m is satisfied. Okay, so the assumption on pairing between n and m is 0 is exactly the condition which guarantee that this vector field is divergence free, which at the level of the transformation means that the transformation is volume preserved. Okay, so if you glue tori according to birational transformation of this form, the holomorphic volume form will be preserved and the Calabi-Yau condition will be preserved. Okay, so for every mn satisfying these conditions, you can consider this transformation. And in cluster theory, to define cluster varieties, we need to know how to iterate this transformation. We need to know which, we want to know which are the nm we want to consider. And this combinatorics is encoded into some kind of initial data, which are called fixed data. And to not have too complicated notation in this talk, I will restrict to so-called skew-symmetric fixed data. So in the most general theory of cluster varieties, the most general fixed data is something called skew-symmetrizable. But discussing this more general situation involves much more notation. So for this talk, I will restrict to the so-called skew-symmetric case. So fixed data is the following. It's the data of a lattice n, as before, with an integral skew-symmetric form that I denote by this curly bracket. So it's a bilinear form from n cross n to z. It's integer value and is skew-symmetric. And the second piece of data is a saturated sublattice nf inside n, where f is some index for unfrozen. And just for notational purposes, we'll denote by I some index set of cardinality the rank of n, and by IF a subset of I of cardinality the rank of this sublattice NF. And finally, a seed data, S, for this fixed data, is an extra data of a basis, EI, of the lattice n, so indexed by this set I. So is that if you restrict this basis to the EI with I in the index set IF, it is a basis of a sublattice NF. And so just a matter of terminology, the basis element EI with I in IF are called unfrozen basis elements. And the one where I is not in IF are usually called frozen elements. Okay, so it's very simple data. You have a lattice, you have a basis, you have a division of the basis element into frozen and unfrozen, and then you have the skew-symmetric form on the lattice. And so further notation we will use once you have all this data. As before, I will denote by M the dual lattice. I will denote by EI star the dual basis of M. And I will denote by VI the element in M obtained by evaluating the skew-symmetric form at EI. Okay, so the skew-symmetric form is a bilinear form on M. So if I evaluate on EI, I only get the linear form in the second entry, meaning an element of the dual M. And now out of this data, it's possible to define two cluster varieties, X and A. First of all, we define tori, XS and AS, attached to this seed. And XS is simply the torus Tm with co-characteristics M or characteristics N. It is a torus whose coordinates, sometimes denoted by big Xi, are the monomial Z to the EI. EI is the basis of N, so they give function on this torus. Whereas AS is a torus Tn with co-characteristics N, characteristics M, and which has natural coordinates AI, given by the monomial Z to the EI star, where EI star is the basis of M, dual to EI. And just some remark, you have this Q-symmetric form on N, and because N gives you functions on XS, this bracket naturally induces a Poisson bracket on the ring of function. So actually this torus naturally come with a Poisson bracket. And on A, you have something dual in some sense. You have a bracket at the level of vector fields, meaning you have a two form on this torus. Okay, so until now we just have tori, two dual tori attached to a seed. And we want to produce more tori by modifying the seed. And this operation is called mutation. So if you have a seed S.
Something, sorry. So
sure.
The pairing that you use on N to get the Poisson is the curly bracket, right?
Ah, you are perfectly right. I'm always mixing myself because in some contexts I'm using one or the other, but you are perfectly right that here it is a curly bracket. Exactly. I'm sorry. Thank you. Yes. Yes. Okay, so what is mutation of a seed? It depends on the choice of unfrozen index k, and then you can define mu k of s. So it's just a new basis, ei prime of the lattice n, and it is defined by this explicit formula. So if I is different from k, you replace ei by ei plus a multiple of ek, where this multiple is a positive part of the pairing between ei and ek, where positive part means max between this integer and 0. So it is 0 if this thing is negative, and it is this integer if this integer is positive. And finally, ei prime equals minus ek for I equal k. So you have this mutation operation at the level of basis ei, and so you have induced transformation at the level of monoid algebra, and so at the level of tori. You have also operation at the level of the dual basis, and so you have induced birational maps uk between the tori attached to the seed S and the tori attached to this mutated seed uk of S. And here are the explicit formulas for how this mu k acts on function. So this thing is for x and this thing is for a. Where, yeah. And you can check that indeed this transformation are special case of the general volume preserving birational transformation I was mentioning here. Where here some of the pair of elements you consider are ek and vk, and here it is the same but somehow reversed because it is for the dual torus. And the volume preserving condition is that we should have ek vk is 0 is true because vk is obtained from the skew symmetric pairing with ek, and so by definition this quantity duality pairing between ek and vk actually is a skew-symmetric pairing of EK with itself, which is 0 because skew-symmetric pairing is skew-symmetric. So indeed, this transformation are volume-preserving transformations. And you can write, is there a question?
Not from here.
Okay, sorry, I heard something, but okay, let me just continuing here. I just wrote so you can, so out from this formula, recalling the definition of xi as being a z to the ei, and ai as being z to the ei dual, you can work out these explicit formulas, which are the ones which are often used in the cluster algebra or representation theory literature, and which maybe looks a bit complicated, but at the end of the day come from this maybe simpler looking formula, and which are just particular case of the general volume preserving birational transformation here. So now, how do we get the cluster varieties?
I'm sorry, how can something so complicated as the second one come out of the, I've seen this formula many times, but now I'm looking at it and I can't understand how it can come out so complicated, the A formula.
Yes. Yeah, I don't know if I have something simpler to say than to say that one needs to do the computation, but I think it has to do with the fact that, I mean, we need to take some dual basis. And I think that, in this transformation, we have z to the v chi. So I think the thing which will appear naturally in this formula will be something like z to the vi, where vi is in M. But to express it in terms of the AI variable, you need to express this VI in terms of this dual basis EI dual. So I think you need to write something like VI probably the sum of
I see.
EJ dual, probably, and probably you get something like that.
Yes.
So at the level of variable, you will get something like that, which will appear.
Yes, thank you.
It comes from this VI element.
Yes, the going from VI to EI star is what makes it complicated.
Yes, exactly. You have this kind of two bases, a natural dual basis, and the dual basis given by the skew-symmetric form, and you need to compare them, and it produces these kind of expressions.
Yes.
Okay, so how does it work? You start with a seed S. You have one torus, let's say XS, and then you look to a mutation of this seed at some index K, you get a new torus, and you glue them together according to this birational map. And then essentially you iterate this operation by first of all considering all possible mutations of the initial seed for all possible unfrozen K, and then you iterate. You consider a mutation of the mutated seed and so on. So in general, you get some kind of collection of seeds which are really indexed by some kind of tree. And it's a tree which at every vertex has some kind of cardinality of IUF branches corresponding to all the possible index K, so all the possible way to mutate. And then you iterate. So here I'm assuming that the cardinality is 4. So something like that. And then for each vertex of this infinite tree, you have a torus. And then each time you have an edge, you glue this torus according to the corresponding birational map. So I should say that in simple example, actually this mutation somehow come back to itself, they come back to the identity. So in some simple examples, you actually glue only finitely many tori. But in more complicated example, you might have to glue infinitely many tori. Okay, so this thing is a definition of X and A as schemes. And cluster algebras are essentially algebra functions, regular functions on these schemes. And maybe the other thing which are more properly called upper cluster algebras in the cluster algebra literature. And here there are some warnings that this kind of operation of gluing infinite tori definitely always produce a well-defined scheme, but it can be a bit of a pathological scheme. And in particular, X might not be separated. So it's a fact that A is always separated. And the related slightly maybe pathology looking is the fact that these cluster algebras might not be finitely generated. Okay, because definitely the algebra function of torus is a very nice finitely generated thing, but when you start to glue things, infinitely thing, it's unclear that the result is finitely generated. So again, in very like nice example where you glue finitely many things, you can get some very nice algebraic variety where everything is finite and nice. But in complex generality, you might get slightly weird phenomena happen. But for many purposes, as I will describe in one moment, we do not necessarily care about these schemes by themselves. Sometimes you only care about these schemes up to codimension 2, which, for example, is enough if what you really care about are the algebra functions. And I will give in 1 minute an alternative point of view on these cluster varieties in which you get slightly different algebraic varieties, but which looks much less pathological in general. So actually, I think I will skip that for now. I will come back to this slide much later. Yeah, I'm coming back to what I just said, to some of the log-Calabi-Yau variety point of view on cluster varieties. So until now, I've described cluster varieties as non-compact Calabi-Yau varieties that you can cook up by gluing tori together. But in this code, we already saw in many talks that there is a pretty different way to cook up non-compact Calabi-Yau variety as open part interior of log-Calabi-Yau pairs. And we saw that one way to cook up log-Calabi-Yau pairs, so the one admitting toric models, is to start with a toric variety and then blowing up hypersurfaces contained in the toric boundary of the toric variety. And then by taking the strict transform of the toric boundary, you get log-Calabi-Yau pairs. And so you get log-Calabi-Yau pairs, so maybe so XD obtained from some toric variety X sigma D sigma by appropriate blowup. And then the complement X minus D is an example of non-compact Calabi-Yau variety. And so what Gross academically realized is that the cluster varieties actually fit into this framework of log-Calabi-Yau pairs obtained as blowup of toric varieties. So here is an explicit recipe. If you want to recover the X cluster variety, you start with a fan in M containing the rays spanned by the vectors VI. So remember, VI was this EI pairing with EI. There were elements in M, and you can consider the rays spanned by this VI. And you consider any fan containing these rays. So it depends exactly what you want to do. If you really want to have a nice, at the end of the day, to have a log-Calabi-Yau pair with a smooth projective compactification, you just take as a fan any smooth projective fan which contain the rays VI. You might add extra rays, it will change the compactification, but it will not change the interior at the end of the day. So pick any fan in M containing these rays. This defines a toric variety. And each of these rays corresponds to some boundary component Di in my toric variety. And now inside Di, you will blow up the hypersurface Hi defined by this equation. 1 plus z to the ei to the power index of vi equal to 0, where index of vi is the index of vi inside the lattice M. So it is the biggest integer dividing vi as an element of M. So it is a 1 if the entries of vi are coprime. Okay, so you can check that this equation kind of makes sense because ei live in N. And so monomial z to the power something in N indeed function on the torus, on the big torus for a toric variety with span in M. So this thing is indeed a function, or Rush function on our toric variety. And you take its restriction to di and you look to its vanishing locus, you get some hypersurface in the boundary divisor di, so something of codimension 2 from the point of view of the total toric variety, and you can blow up this locus. And you call X the blow up, and you call D the strict transform of the toric boundary. Then you get some log Calabi-Yau pair, and I denote by UX the interior, so the complement of the divisor for this log Calabi-Yau pair.
But this is not always non-degenerate, right? It's a Poisson structure we have on X, right?
Ah, yeah. So maybe it is a good point. Yeah, maybe I will get confused in one moment. So it's true on X there is always a Poisson bracket, which might be degenerate. So definitely we do not have in general symplectic 2 form. But I think we always have a holomorphic form.
Volume form?
Yeah, volume form, like top form.
But isn't that, wouldn't you expect that to be kind of equivalent to, like if the power is a volume form, then that already implies that you have a.
Yeah, so I think it's true. So probably, yeah, I agree. I'm slightly confused about what's exactly happening, but I don't think there is a contradiction because, yeah, it could be the power of the 2 form is not a volume form, but still there might exist another volume form.
Yes.
Like even if I just take a standard torus C star to the N, and if I write down a skew symmetric matrix with some kernel, this thing would just be a 2 form on a C star to the N, which might be degenerate. For example, this N is odd for obvious reason, but still on C star to the N, there is a holomorphic volume form.
Yes.
So, yeah, and this holomorphic volume form from the gluing tori point of view, it comes from the fact that this transformation preserves the volume form. And from this log Calabi-Yau point of view, it comes from the fact that this boundary divisor is anti-canonical, so in the complement you have some volume form.
Yes, but from this picture, we don't recover the Poisson structure.
Yeah, so actually, I mean, you could recover it. So I did not, okay, I'm not going to explain it. I was not planning to explain it, but I think you could.
No, you can skip if you were planning. If you say just yes, then I will ask you later or okay myself. You can skip it if you're planning. Okay,
let me just say, yes, this blow-up is so particular that you could argue that the Poisson bracket will exist.
Oh, okay.
Okay, so this thing is for X, and for A, we do the same thing, but everything was kind of dual. Now you have a fan in N, and you consider the res span by this basis element EI, and now you blow up hypersurfaces with equation involve VI. And so again, you get some different log Calabi-Yau pair, and you denote by UA as a complement. And now the main theorem of Grossack and Kiel paper on cluster variety and birational geometry is that if you do that, this UX recover X up to codimension 2. So the claim is that there is some birational isomorphism between X and UX, whose indeterminacy locus is of codimension 2. In particular, algebra functions on x and ux are the same. And under a technical assumption that I will not discuss, the same thing is true for A cluster varieties. Okay, so the upshot is that there is these two different points of view on cluster varieties. Either you glue tori, that is rational transformation, or you have this log-Calabi-Yau point of view. You start with a toric variety, you use some blow-up operations, you get log-Calabi-Yau pair, and the complement is essentially the same cluster variety. So I will only give a picture of the simplest case to understand why are these two things the same. So what is somehow hidden inside the proof of this statement. So essentially what one needs to understand is why, if we construct this log-Calabi-Yau operation by doing these blowups, why is it true that the complement U, why is it true that the interior part of this log-Calabi-Yau pairs, why is it true that it contains many different tori? It is essentially what one needs to understand why to make contact with the description by gluing tori. So what is obvious is that if you start with a toric variety, you do the blow-up operation, then in the interior of the blob geometry, there is an obvious torus, which is simply the pre-image of the big torus inside the toric variety. What one needs to understand is where are the other tori corresponding to the mutation operation. And the simplest example, and in fact what is behind actually the general result, is a series of elementary transformation of P1 bundles, and which at the end of the day kind of reduce to some kind of elementary birational geometry of surfaces. And here I just wrote down a picture of what happens in the simplest case. Let's assume you start with a toric surface, which is P1 cross P1. So here I draw some squared, which is some kind of toric picture of P1 cross P1. The black square is a toric boundary. And in the complement of this black square, in the interior of this toric variety, you have some torus C star squared. Okay, so this thing is a standard toric picture. Now what I'm doing is that I want to produce a log-Calabi-Yau pair by blowing up a point somewhere on the boundary of this toric variety by picking a non-toric point. For example, the point, I pick the point here. I blow up this point. And when I do that, I create an exceptional divisor, which is one of these red curve here. So by construction, inside this new log-Calabi-Yau pair, in the complement of the boundary divisor and the complement of the exceptional divisor, I have a torus that I try to still draw in green, C star squared, which is just a pre-image of the previous C star squared in the toric situation. Okay, so away from this red point, the blow-up does nothing. So I have still the same torus C star squared sitting inside my new geometry in the complement of the exceptional divisor. So this thing is some of the obvious thing. I have some a torus in something toric. I blow up, I still have the same torus. The thing which is maybe not completely obvious is to realize that in this geometry there is a different torus. And it comes from the fact that my original geometry was actually, I can view it as a P1 bundle. I draw in black vertical lines, which are P1 fibers in this geometry. And when I blow up a point here, it is living on one of these black fiber. And so in a blow-up geometry, I can look at the strict transform of this black line. And this strict transform of this black line is what I've drawn here as being another red curve. And now you see that in this picture now, in fact, these two red curves play a completely symmetric role. So in the way I cook up this picture, one was special because one was an exceptional divisor and the other was a strict transform of a line. But then I can invert the role of these two things. I can simply blow down the other curve and reverse the two things. And this implies in particular that in the complement of the second trade thing, there is another copy of C star squared that I try to represent in blue. In blue, I try to represent the boundary of a second torus inside this geometry. So the conclusion is that inside this complement of this log-Calabi pair, there is not only one obvious torus, but actually there is two tori, C star squared, and which have some overlap. And if you compute the birational transformation, gluing these two tori on this overlap, you will exactly find some cluster-like transformation. And so actually, see what you get here is one of the simplest examples of cluster variety, where you only have to glue two tori together. I think it is the case, maybe I will say something slightly wrong. If you take n equals z squared, so you have a basis E1 and E2, and you take one to be unfrozen, but you take the other to be frozen. And I think if you take the pairing between E1 and E2 to be 1, and if you compute the A cluster variety for this very concrete explicit seed, you will find that you do not have to glue infinite tori, but only two of them, and it will exactly reproduce this geometry. And finally, I can say why in the statement is up to codimension 2, because actually in this picture, if you think about where are the two tori, one of them is everything except one red curve. The other is everything except the second red curve. So the union of the two tori is everything except the intersection point of these two curves. So actually the cluster variety defined as a union of these two tori and the interior of these log-Calabi varieties, they are the same up to this point. So more in the union of the two tori, there is some kind of missing point, and this kind of missing point is filled in the log-Calabi description. Okay, so I can try to say the same thing in a different way, that in the log-Calabi description, when you have a toric model, you realize the log-Calabi pair by blowing up from a toric variety. And from this point of view, there is an obvious torus, which is a pre-image of a torus in the toric variety. But the same log-Calabi pairs can have many, many different toric models and can be obtained as blow-up of a toric variety in many, many different ways. And so there will be actually many, many different tori inside the log-Calabi pair. And all these tori are all the tori which appear in the description of cluster varieties as gluing.
And like this picture, can it be used, can it be generalized to give like a start with a toric model and then do something and produce another toric model?
Yeah, so maybe I should have drawn some of the other picture, which is somehow if you contract the other curve, then you will recover P1 plus P1, but blowing up this point.
Yeah, and this example I understand perfectly, but I don't see how to implant this example into a more global situation.
Yes, so the point is that in more global situation, like maybe up to doing entirely purely toric blowups, you can always produce this kind of P1 cross P1 structure. So, for example, maybe something which does not look like P1 cross P1, like P2. And I blow up one point on P2, for example. And Yeah, and what we like to what is the analog? So this thing is some of the birational geometric interpretation of the mutation. And here we want to know what is the birational geometric meaning of the mutation. And because it's not a P1 fibration, it's maybe not completely clear what to do. But the claim is that you can always reduce to the case of a P1 fibration up to making a toric blob. So at the fan level, here I have some fan. And to have some P1 fibration picture, if you blob something corresponding to the divisor corresponding to this ray, to have the P1 fibration structure, you just need to add the opposite ray. Yes. So what does it mean to add this ray? It means to blow up this point in P2. So now you get something like that. P2 blow up in one point. And doing this toric blob does not change the interior. So if what you care is a non-compact alveoli, doing this operation is harmless. And now on this blob geometry, there is a P1 fibration structure.
Yes. Okay, I think I understand this one as well. What I still don't understand is that there is this middle picture where you also describe the gluing of the two tori.
Yes.
In the P1 fibration local picture.
Yes.
Can one make sense of the middle picture? Like, does that mean anything?
I mean, definitely you can see a similar picture here, right?
Yeah, but that's not a cluster variety or anything like that, right? It's just some random picture that appeared in our construction.
No, I mean, in some ways, this thing, okay. I mean, the complement of the red square, the complement of the red thing is a picture of our cluster variety. It's just that I've drawn various stuff living inside the cluster variety.
But is also this, so I'm asking because now the exceptional divisors coming out of different edges actually intersect in that middle picture, in the global situation. But that's not something that you see when you do toric blow-ups. They never
Oh, okay, yeah, so it's the point that these red things, there are not two exceptional divisors in one blob. Actually, one red is like one exceptional curve for one toric model, and the other red curve is an exceptional curve, but for a different toric model. And the existence of these two tori is related to the existence of these two different toric models.
Okay. Thank you.
Okay, so here I just have one slide. I will not spend too much time about it, just to give. So actually, cluster varieties appear in many different contexts. But in one moment, I will talk about the Fogg-Gontroff duality conjecture, and I just wanted to give a small idea of what kind of question Fogg-Gontroff were thinking about when formulating their conjecture. So they were talking about moduli space of local systems on topological surfaces. So really, S is a topological surface. So now it's no longer algebraic geometry, it's just topological surface with some, let's say, compact with some genus, and maybe also add some mark points, which are some kind of punctures. And now if G is an algebraic group, a complex algebraic group like SLNC or GLNC, you can construct some interesting algebraic variety, the character variety, by looking to representation of the fundamental group of your surface inside this complex algebraic group. And you consider such a thing up to a conjugation action of the group. And because G, so it's a complex algebraic group, something like SL2C, for example, it's an affine algebraic variety. And the fundamental group is something like with finitely many generators and relations. So actually, this space of representation will have a natural structure of affine algebraic varieties. And if you take the appropriate quotient in the appropriate algebraic sense, you still get some affine algebraic varieties. And these algebraic varieties are interesting from many, I mean, they're related to many different things, and so you might try to understand them. And the remark, I mean, what appears in the work of Falk and Gonchorf is that there are moduli spaces which are not exactly this moduli space, but closely related to them. So this moduli space will be called usually the character variety, or maybe the moduli space of G local systems. And this thing in general is not a cluster variety, but if you modify the definition a little bit, so I will not go into the details, if you consider framed G local system, or if you consider decorated, twisted local systems, then you get as moduli spaces affine algebraic varieties. And the main result of Gonchorf and then follow-up work is that these algebraic varieties are natural structure of cluster varieties. So here, what does it mean to have a cluster of what does it mean to have a structure of cluster varieties? It means that you can find tori birationally embedded inside your space. And so you essentially torus charts on this space, and the transition functions between these charts are as prescribed in the gluing of the cluster varieties. So in particular, these spaces are birational cluster varieties. And sometimes you can be more precise. Actually, it's possible to prove that the X version of this space actually is exactly the spectrum of the cluster algebra attached to the X cluster variety. So in particular, in this example, the X cluster variety or the X cluster algebra is very nice. It's really finitely generated. You can really prove that it is an algebra function on a very nice finitely generated affine algebraic variety, which has a nice origin as moduli space of local systems. And I'm sorry that I was not able to attend the previous talk in this school today, but it might be that the discussion of the previous talk on the Schender-Treumann cluster construction might be related to this story, or how cluster structure come from thinking of variety as moduli spaces of local system or recursions. Okay, so this thing was just a motivation, like one context where cluster varieties appear, and it was thinking about this context that Falk and Gonchorf came up with their duality conjecture. And it is a conjecture which is phrased using so-called sets of integral tropical points, x trop z and a trop z of x and a. And there are various possible ways to define what tropicalization means, but in some previous talks in this school, we saw one way from the log Calabiot point of view. We saw tropicalization defined as a union of cones due to the various strata of the divisor in the log Calabiot compactification. And so for X and A, because they have toric model, if you fix one toric model, the tropicalization is essentially identified with a fan of the toric variety. And so the set of tropical points of the X cluster variety, if you fix a seed or a toric model, it can be identified with the points of the lattice M. And dually, the set of tropical integral points of A is identified with the lattice N. And then the Falk-Gonchorf duality is something relating X and A, and it predicts that the algebra of regular functions, let's say on X, should admit the canonical basis indexed by the set of tropical points of A. So maybe stated like that is not a fully precise conjecture, because Okay, it does not really specify uniquely what one wants, but at least it's an indication of what we want. So what is it about? It's about basis. So it's really basis, it's like linear basis. So you consider the regular functions, they form an algebra, but there is an underlying vector space. And you want the basis as a vector space over the base field. And you want this base to be canonical. So in particular, it should be invariant under all possible automorphism of your algebraic variety. So for example, in this topological story, there is some very interesting action of the mapping class group of this surface on these moduli spaces of local systems. And so in this context, you want these, the prediction is that there should exist a basis which is invariant under the action of this mapping class group, which is something very non-trivial because a mapping class group might be very big and act in a very non-trivial way. So let me first give the trivial case of this conjecture, which is good to have in mind to have an idea of what we're talking about. If the cluster variety consists of a single torus, so if the cluster variety just C star to the n, let's say X is just spec C bracket n. Then a torus has a canonical basis given by monomials. Monomials Z to the n for n in n. It's a basis, I mean, that's simply the Laurent monomial forming a basis of the algebra of Laurent polynomial in some variables. And the point is that the lattice indexing the element of this basis, by definition, it is a character lattice of my torus, but by definition of duality, it is the same thing as a co-character lattice of the dual torus. And so this n is really, and this co-character lattice of the torus is really the set of tropical points of this torus. Okay, so in the ordinary case of tori, so this conjecture try to generalize the elementary fact that for tori, we have canonical basis given by monomials. And monomials on one torus are indexed by the character lattice, which are the co-character lattice of the dual torus. And so the prediction is that somehow for general cluster varieties, there is some kind of generalization of the monomial functions for tori. And the prediction is that they should be indexed by integral points of the dual cluster variety.
Is the intuition that a U-trop kind of being kind of like a base of a special Lagrangian vibration still true here? Is that a good intuition to have for A-trop and X-trop?
Yes. So yeah, indeed, they are the same, yes. Yeah, and actually, okay, let me say some maybe very vague sounding statement. There is a way to maybe motivate these conjectures, this existence of particular basis, from a more like torus vibration point of view. And this, okay, it will be extremely vague. This conjecture has to do with the so-called maybe semi-classical limit or Bohr-Sommerfeld approximation. When you try in symplectic geometry, if you try to construct, for example, a section of some holomorphic line bundle, then in some sense, it's a kind of quantization problem, and in some appropriate limit, it should have some kind of semi-classical description, which should have something to do with something like integral point on the base of the torus vibration. So, okay, I guess I'm trying to say something which maybe in the toric situation is much more familiar, that in torus in a toric situation, if you have a polytope, integral points of the polytope correspond to bases or space of sections of ample line bundle. This thing is a completely clean statement for toric varieties. But you might try to understand this statement really from the geometry of the torus aberration on your toric variety. And you might try to hope that this kind of argument should admit generalization for more complicated singular SYZ type torus aberration. And that you might still expect to have natural functions of sectional line bundle indexed by integral points on the base.
This is some kind of Bayesian toplets quantization.
Yes, that's right. So this quantization has many names, but I think Bayesian toplets is one of the relevant names. Yes, exactly.
That's very interesting. I'm very curious.
Yeah, and actually, I think this. I mean, it's written somewhere as a motivation, but I think it has, as far as I know, this precise relation has never been. I mean, this relation has never been made precise. I mean, yeah.
But what's a place where it's mentioned?
Yeah, is it really? Yeah.
No, I'll email you.
Yeah. You can email. Yeah. Okay, so I will just end by saying a few words about this conjecture. First, remark that actually this conjecture is not true in complete generality for some kind of easy reason, and pray just for control for thinking about their geometric setup for which it should be true, but in complete generality might not be true for some kind of slightly obvious reason, which are actually these varieties do not have to be affine, so they can have very few regular functions. So for example, I guess yesterday in Phil Engel's talk, actually this Looijenga conjecture is exactly about the case of log-Calabi-Yau surface where the boundary is very negative. And so the interior is very much non-affine and has no non-constant regular function at all. And actually this thing can be realized as cluster varieties. And so in the case where there is no regular function at all, in particular, you do not have basis indexed by a dual lattice because you just have no function. So for the conjecture to be true, you need to have some kind of positivity assumption on your boundary, or you need your variety to be appropriately positive, like affine. And I will finish by mentioning that to essentially growth I can kill, mentioned in the paper that this Fogon-Shorf duality conjecture is the existence of canonical basis for cluster varieties, which, so formulated by Fock and Gonchorf in the cluster context, actually should be a particular case of a much more general statement for any log-Calabi-Yau varieties, where the duality is between the log-Calabi-Yau varieties and its mirror log-Calabi-Yau varieties. That somehow the existence of this basis should not really be related to the cluster structure, but should really be related to the log-Calabi-Yau property and mirror symmetry.
But also positivity, right? Without
that's and so with the appropriate positivity statement. And in fact, this mirror symmetry picture actually gives a hint for actually what goes wrong when you are not positive, and how to modify the statement to have a statement working in general. So. Okay, so using mirror symmetry inspired techniques like scattering diagrams, broken lines, and functions, Grok technically conservage, and then Kill and Yu using maybe different kind of mirror symmetry ideas. And so with slightly different assumptions, roughly proves that under appropriate positivity assumptions, the Fogon-Shorf duality conjecture holds. So there is some kind of, so what they're doing is out from some combinatorially defined scattering diagrams, they're able to cook up the basis of functions on the cluster varieties and to prove that they're canonical and they're indexed by the expected sets. And I will just finish by saying that if you do not make the positivity assumptions, there is always a formal version of the duality conjecture which always holds. And in some way, this formulation is a bit natural from the mirror symmetry point of view, because in mirror symmetry, you only expect clean statement only near large volume limit or large complex structure limit, meaning in general, you should not consider one mirror variety, but a family of mirror varieties. And things nice really happen near the special fiber of this family of mirror or mirror varieties. And there is something similar happening for cluster varieties. You can cook up a nice deformation of the A cluster variety called a prime cluster variety, the cluster variety with principal coefficients, with degenerate A cluster variety to a torus. And then in the formal neighborhood of this torus, the Fogg-Gonchar conjecture is true, meaning if you do not look to regular function on A, which might be empty or like a constant, if you look to regular function on this formal neighborhood of this torus, there is always a lot of function there. And then the general statement of Grosser-Kenkiel-Kontsevich is that this algebra function always admit a canonical basis indexed by the correct set. And the point is that when you have positivity assumptions, you can go away from this formal neighborhood to a true family to recover a more conventional statement. And I will stop there. Thank you for your attention.
Any questions? I have to charge the computer before it dies. Okay. Okay. Yes. Any question? Yes.
So there you mentioned cluster structure on trained local systems on surfaces.
Yes.
Right. And then you said it actually relates to the Williams construction. Right?
Yes. It was what I said. So unfortunately, I missed your talk, but yeah, I think it should be, I mean, it's the same, or it should be the same. I mean,
okay, now you consider micro shifts, right? There's a surface, and there's some curves, and there's a micro shift condition in your curve. So you mean those conditions correspond to frame data or something?
Yeah, you seem to have like points taken on the Riemann surface.
Yeah. It's because I only wanted to state the simplest version. And in it, there is a modular version when you remove boundary, like when you have disk and mark point on the boundary, which are related like to wild character varieties, and which also have cluster structures, and maybe they are more directly related. So I don't remember the details of Schindler-Traumazer, but definitely in one of the story, like for example, they have some like micro local sheaves, and maybe in the simplest case, the singular support has to do with a knot maybe, or a curve drawn somewhere on the surface.
Yeah, but it's different. Like the curves don't have to be contractible, for example. Like it's not, you can take a curve that's a meridian of one of those holes. And grow.
Okay. Yeah. So you're saying maybe the construction is more general in a sense that.
But there are no punctures or anything like. There are no. I don't think there's a role for the X's.
There's no punctures.
Yeah. There's no punctures or X's. Either of them. They don't exist. It's just these red kind of curves.
And I was wondering maybe those someone can be interpret by some curves. I don't know.
Yeah, I think it seems like a good thing to look at.
Yeah, exactly. I don't know if there is a precise comparison written somewhere. I mean, because I think definitely in the paper Schindler-Traumazer, I mean, they say that the construction of cluster structure is, I mean, very much related to cluster structure and character variety and wild character variety. But I don't know if there is a like precise comparison, like matching all the technical details. Yeah, framed, decorated, twisted, mark points. I don't know if it has been done. I'm not sure.
Thanks. Yeah.
It's a great question too. Okay, other questions? Okay, so I have a question. So I agree like that some kind of mirror symmetry says something like the statement should look like this formal statement. Mm-hmm. But I think kind of the magic of this conjecture and the like this complex mirror symmetries, it should be two-sided, right? It should like, is there any hope of like, you know, you have something, you construct some formal mirror, but like, can you make sense of symplectic geometry on this formal mirror or something like this, like Kähler forms? Is there anything in that direction, or?
You mean to be able to go both way, to go back, or?
Yeah, to reverse the roles in the two sides.
Yeah, because so I think this formal thing, maybe it's expected that maybe they exist, like maybe analytically.
Yeah, I mean,
and then maybe symplectically they really exist as maybe appropriate domain, and then you might do symplectic geometry.
I mean, I saw like in the Hacking Keating paper.
Yes, exactly. Yes.
But they just say something that's impossible to understand. They just say, "Oh, you can do something," and then they don't say. Like I've never seen that.
Yeah. So I think, I mean, in dimension 2, in the paper, actually, Gross and Kiel prove something non-trivial about their construction, as they really prove that the formal thing actually like converges in some way. Like not in an algebraic way, but in some kind of analytic way.
And it also comes embedded somehow, so you can maybe think that, but it's kind of it's really difficult to believe that what they did there is some general structure. It just seems like kind of it somehow worked.
Yes. So in complexiality, I don't know, especially for this kind of log or non-compact. Like, I mean, maybe like for compact Calabi-Yau varieties, I will be much more.
Yeah.
I think it's much more clear what you expect. Okay, maybe it's formal, but after an appropriate holomorphic change of variable, actually it will converge, and maybe, I mean, definitely you expect a non-zero radius of convergence, and maybe in correct coordinates it become algebraic. But for this kind of non-compact thing, I'm not fully sure.
So, but what you do with Hülya and the new paper is not, in what sense does?
Okay, yeah, so yeah, and I will talk about it next week at the conference. So what we are doing is you can start with one cluster variety and run some mirror symmetry construction, the one of Gross and Siebert, and you get some formal family. And actually, what we are doing is to compare this formal family with a formal family which appear in this statement of the formal Forganshof conjecture. Because here I say, okay, maybe motivated by mirror symmetry, there should be something formal. But actually, what is really proved in the HKK, you see this formal family. And so what we are doing is, in which sense is this formal family really the mirror of the starting cluster variety?
Okay.
And actually, the answer is a bit tricky, in the sense that this thing is not on the nose what most people will call the formal mirror family, but to go from.
It would be a shame if something was true without modification for once, right? Okay,
yes.
So
and maybe it's a bit related to your question, somehow to prove the comparison between the two formal families. Actually, you need to prove that one formal family somehow converge on some region which is bigger than naively expected somehow. And somehow there is really some kind of algebraic thing which interpolates between two formal families. And the fact that there is this kind of algebraic extension somewhere is like non-trivial.
Okay. So yes, we're gonna see a lot of talks next week leading to that talk. So like 4 talks after 4 talks, I don't know how many people will stay alive in this room, but
yeah.
Okay, thank you very much. Is there any online question?